For coming. I'm Jamie. I work for Google in Sydney. I want to apologize before I start. As I've come from Sydney, I'm feeling very jet lagged, which is two side effects. One of them is at 2 a.m. I was working on my slides, and now I am hitting the wall, which means I probably don't remember what I did to my slides. Anyway. If you were in Charity and Bridget's talk earlier, you would have heard Charity say that observability is your rock, your foundation of your service. And I agree. Mikey Dickerson, who left Google to join the USDS, came up with this chart, which is we call it Dickerson's hierarchy of needs, reflects Maslow's hierarchy, which says basically you can't do anything serious with your service unless you have monitoring, because all the other things rely on you to be able to ask questions of what you're doing. So I think this is a very important thing. I think he agrees. I think Charity agrees. I think we all agree. A long time ago, when I first started giving a variation of this talk, monitoring sucks was a big theme. I'm not sure if people still feel that way. I assume that they do. My opinion on why this sucks is when it's difficult for you to modify the monitoring to respond to the size of your service as it grows or as the requirements change. So you can't improve the quality of the alerts you're receiving, and you can't improve the tools to help you debug and understand why either the monitoring itself is broken or the system you are trying to monitor is broken. I am not a fan of Nagios or its spin-offs. This is my personal opinion. This does not reflect the opinion of the company. But I do believe that the pattern of a check and interpret the results as a independent thing that gets run in isolation is wrong, because I think it's expensive in terms of compute and the resources required, and it's also expensive in the hours you spend to maintain the configuration, which goes against these tenets I've just said before, that you have to make these things cheap to operate to scale to make it not suck. At best, I think these check tools are a great front-end programming system, so it becomes part of your complete breakfast, which is also a nice way of saying this particular breakfast contains only sugar and you probably shouldn't eat it. All right, so in general, why does anything in ops suck? It's because it doesn't scale sublinearly with the rest of the service as it grows. We would like to not spend as much time doing the things we used to do as the service gets bigger. And so every time you find yourself hitting that inflection point, or perhaps the curve isn't as linear as you hoped, that's the opportunity for you to start going, okay, how can we re-engineer what we've got and build something that's more palatable, I suppose, to the size of the service now, so that the time humans are spending doing this work is less or about the same constantly as we get bigger. So, turn-ups, turn-downs, refactoring of code, onboarding of new customers, incident response, all of this work can't continue to cost more as the service gets bigger, because it just obviously gets very expensive. So I guess the general principles are like what Google says in the SRE book. We should be spending less than 50% of our time total on ops work, and everything else should be spent on making that stuff go away. Oh yeah, so blah, blah, blah. High-level languages. It's kind of where I'm heading with this. Monitoring is a large space. There are a lot of different things it means to different people. I was at Monitorama and I was very surprised to find that not everybody thought monitoring was what I thought it was. But let's say there's 4 things. And this is my list, so obviously it's not necessarily true, but it's true to me. And I've put them on this little graph of where I think things fall in terms of how recent the event was versus how tight your measurement granularity is. And it's obviously it's a very big space. I am only going to talk about this little bit. Now, with any luck, this bit actually works. No. Go back. Play the video, please. No. Oh. So much for testing. And we don't even have it anymore. Anyway, you may be familiar with The Simpsons. That's going to... It's really... And now... my slides have completely stopped. Here we go. Okay. I guess everyone uses Keynote on Mac OS, and that just works. And here I am using Google Slides. If you're familiar with The Simpsons, you might remember Barney saying he's worried about the beer supply because after this case and the next case, there's only one case left. And this is obviously a very easy thing to model with a threshold-based check model. As the number of cases of beer changes over time, we can compare that number of cases to a threshold that Barney considers worrisome. And if we fall below that threshold, we can send an alert. If you were to program a modern monitoring system to do that, you might write it like this. But some alerts don't map very well to this simple threshold model. And you might have been paged for running out of disk in the past, and you might go, well, that's bad. Maybe I'd like more notice about that. Maybe you go, hang on, I don't need to care about this alert right now because disks have gotten really big in the last many years, and there's actually quite a lot of space left. So what is it do I really care about a disk? Maybe I care because I need to go and get a new disk, and I need to run down to the shop and buy like an external USB drive and plug it into the server before the disk gets full. So really what I care about is how long do I have to respond to the thing going super critical, and kind of balance that time for recovery against how much time should I have left before we page. So how much time do I page before the event gets bad? So how would you do that? And the answer is maths from high school. And just in case any teachers are watching, when your students say, am I ever going to use this in the real world, you say yes. So this is a clip from Speed, and obviously it's not going to work, so I'm not even going to try. But pop quiz hotshot, there's a bomb on the bus. When the bus speeds up, the bomb is armed. And when the bus slows down below 50 miles per hour, the bomb goes off. What do you do? So Dennis Hopper's alert cares about once the bus has increased velocity over 50 miles per hour, because at which point the bomb is armed. And then subsequently, once the bus slows down, the bomb explodes. So we've got two alerts going on, and one of them depends on the first one having latched true at some point in the past. You might program those like this. Let's pretend that you had a language in which you could say, I want to know if this vector goes over 50, and then I want to know if this other vector that depends on that previous vector, somehow we've recorded its state over time. And we want to know if that alert bomb armed was firing in the last day, and now the speed is less than 50 miles per hour. Keanu, on the other hand, wants to know what bus it is. So he should start trying to save the bus, obviously right away, because, people's lives are at stake. But he really knows that he has to start thinking about saving that bus once we go over 50 miles per hour, because now we know we're in a time-critical situation. But it doesn't really matter how long it takes to save the bus, as long as the bus is above 50 miles per hour, right? So it only starts to matter once the acceleration of the bus starts to go negative. We do want to know really that it's rapidly decelerating, because that changes how much time we have before we need to respond. And so take the derivative of velocity, acceleration, mumble, high school maths. And this is Keanu's alert. If the rate of change of velocity, I'm not even going to try to explain that because it is high school maths, and like I said, the jet lag. There is some threshold of time that Keanu, probably having drilled as a police officer, knows how long it takes to save a bus. So we set that to a threshold, and then the maths just kind of works out. Yes. Distributions are a great way of storing numbers of things that happened around the same time with varying values, and we can bucketize them. And perhaps, as Brian Fantana once told us, 60% of the time our request latency works every time. But quantized buckets present a new problem for us. The 10 samples on this slide, what would you might say the 90th percentile of those samples are? We might say it's 6.5 milliseconds if we have perfect knowledge. But if we've quantized all that information away into an exponential bucketing that you might do, then all of a sudden all that information is lost, and we can only extrapolate what that value is. And so if we try and compute what a quantized histogram's percentile is later on, then we can only do a best guess based on the data available. So we might say that the 90th percentile might only be 7 milliseconds, which could be wrong. But we do know where the boundaries are, and so instead we can invert the maths and say we know what the percentage of calculations that fell under a hard bucket limit are, and we know that 60% of the requests are under 2 milliseconds. And let's say that 2 milliseconds is the response time in which we say our service is available. Brian Fantana was right all along. So as the requests come in, we can increment the count of the buckets, and we get like this rate of change graph here, where the 8, the 4, the 2 buckets. You can see how they change over time. And then we divide the values on those lines by the total number of values at each time, and you can see that the 8 line hits 100%. So obviously 100% of the 100th percentile of request latency is less than 8, so they all fall into that bucket. Then the 4 bucket varies over time as things go in and out of those buckets, and likewise with the 2. So Brian Fantana's alert would be to say, tell me when the percent value of the 2 millisecond bucket happens to fall below 60%, and then I want to know about that. I mean, I guess he doesn't really want to know about that. That doesn't seem part of his character. There's some basic principles I wanted to cover before we get into sort of the meaty stuff about alert design, because it's very easy to come up with alerts, it's very easy to program new alerts, but I would like us to also come up with alerts that are useful. Monitoring can suck if you make too many alerts. We want to make the alerts page us on the correct things. So we have this concept of SLOs, SLIs, SLAs. An indicator is just a fancy name for a metric, a thing that we're measuring, perhaps the error ratio or a latency percentile. The service objective is the thing that we want it to do. So we take our SLI and we compare it against a value. And you see I've got 2 examples here. Perhaps we're measuring either the response latency or the error rates over the last 10 minutes, and we have a goal, which is maybe the 3/9th percentile of that latency has to be below 5 milliseconds, or we want less than 1% error rates constantly. The SLA is the economic incentive for us to do that. And internally at Google, it's I'm going to page because that's the relationship I have with my clients. Maybe if you're a public-facing service, you have a monetary incentive to provide a service. Otherwise, you have to give customers some reward, I suppose. Reward's not the right word, but you know what I mean. Side effects of this are the clients will provision against your SLO, whether it's the one you advertise or the one you appear to provide. Jeff Dean wrote a paper. You can read that paper, and he'll say how you can make better, more highly available services when the components you're building on top of are not very reliable. So this is a very good paper. And it's basically saying, you know, if someone can tell you that their SLO is 95th percentile, then you go, great, I can add 2 of them and probably get up to like 98.5% availability, just to pull some numbers out of the air. These SLOs also give us the concept of error budgets. We've said that there's like the inverse of 3/9 time we can have requests go slow, or 1% of the time we have errors in the definition. And this allows us to balance our response time and the amount of work that humans need to do to fix a service in that what's allowed before things get terribly bad. So the SLO is as good as we need to provide it, but it doesn't have to be any better. And we also have to make sure it's as bad as necessary so that we can fix the services and not get paged all the time. 4/9 is 4.2 minutes a month of downtime. And if your pager response time SLA is 5 minutes, then by definition you can't actually ever be in SLO whenever the pager goes off. So you really want to make sure the pager never actually goes off, which is kind of not really going to happen. So in that case, I recommend downgrading to only 3/9 of availability, which gives you a couple of hours, I guess. A colleague of mine wrote a document, and I think the general gist of it got published in the SRE book about what it means to be paged And again, this kind of stuff feeds back into the SLO being provided. But the thing that is paging you has to be customer-facing. Otherwise, why are you doing the work? I have to respond with a sense of urgency because I'm being paged. And the implications of being paged are, I need your attention right now to do something that only a human can do. So if only a human can do it, then it's the kind of stuff that can't be automated away. And it means I have to do something to fix the service. It can't be, oh, that thing that keeps paging that I can ignore, because that boy who cried wolf syndrome means you start to not trust the monitoring system. So nothing can be inactionable. An action might be make that alert go away because it's not providing us any value. If you're going to remove alerts, you can think, oh, I really like that alert because it tells me that the back end is broken. Keep it, just don't page on it. There's all kinds of stuff that's really good for improving your mean time to diagnosis after you get paged by an SLO violation. They'll help you figure out what's really going on. But you shouldn't page on them because they might happen all the time, and it could be within the normal working parameters that tasks crash regularly. So I don't want to page on that. But I do want to know if task crashing is, say, correlated with disks being full. Maybe the tasks are crashing because the disk is out of free space. I am assuming throughout this whole talk that your service has been engineered to be resilient to individual component failures. Because if it's not, then, well, I don't know. I haven't thought that far. Okay, so Prometheus is a tool that I like because it looks a lot like a tool that we have internally called Borgmon. And so I'm going to talk about how Google does stuff with Borgmon, and I'm going to try really hard to make that look like Prometheus. And lots of credit to the Prometheus developers. That's totally possible. Fundamentally, it's a calculator. It just collects values off pages, evaluates some rules that are simple arithmetic, and then sometimes sends alerts and also records that to a time series database. It's really easy to use. Here is how you instrument your client code to be scraped by Prometheus. You say, I'd like a counter, please. And then I increment that counter when I need to. So you export a new handler, slash metrics, for example. I think that's the standard one. And it just has plain text output, if you like, that says, here's the current value of that metric at this point in time. You can add extra labels to individuals, so you can turn these single scalar metrics into tables or large histograms of multi-dimensional metrics, if you like. So time series have types, which is a little bit important because of the way we're going to do the scraping. Counters are really good because they have some nice properties. Gauges are not very good because they have some less nice properties. But if counters are always going up, like the odometer on your car says how many miles, how many kilometers you've driven since you got the car, whereas the gauge will tell you how fast you're currently going. So if we're scraping, I'm not sure if I stressed that enough earlier, the Prometheus model is to scrape a target every interval. And if we're scraping every interval, then we are not going to collect the infinity of points. We're only going to sample it. So when we downsample a continuous curve, we don't really lose any meaning. We can still reconstruct the shape of the curve from those data points. But with a gauge, on the other hand, there might be stuff going on in between the sampling points that we don't ever see. And so we can't really tell them apart. In fact, we lose a lot of useful information. So I think it's better in general to be exporting counters and let the tool at the receiving end interpret those counters. So if you're trying to figure out how to export a gauge as counters, you can potentially export them as two counters. And one of them is all the times you wanted to increase the counter, and the other one, increase the gauge, and the other one is the times you wanted to decrease the gauge. And then the collection system can subtract the two. This is how we typically deploy Borgmons, and it looks a lot like, Prometheus can do exactly the same thing. We have a task, we have a Prometheus, a client web browser, and an operator. Now, Prometheus is cloud native, which is a fancy way for saying it's got service discovery in it, and there's a bunch of different ways you can configure it to find your targets. So you never, ever have to modify the configuration to find new jobs as you turn them up. which is really great for that I don't have to add extra work to do turn-ups. So this comes back to my original point about reducing the complexity of the automation, or improving the automation to reduce complexity. We can add a tool called Alert Manager, which receives alert indications from Prometheus and then sends them off to the correct location, such as PagerDuty, email, Slack channels, etc., etc. Alert Manager can be configured with all different kind of escalation paths, so you can have multiple teams all going into the same Alert Manager, and then it knows that, oh, I got a request to alert someone on the database team. I know who to do that to. And this web serving team is a different group, so they go to the different escalation path. And finally, not finally, but next, time series database for storing stuff long term. And we often run multiple data centers, so we want to stick other Prometheuses around. Maybe a couple at the global tier who watch all of the other ones and aggregate metrics up there. And then you might see complete copies of the left-hand side of the slide in other data centers, as they're built almost identically. And then we just apply more abstraction as the service gets bigger. So maybe we want to put another tier of scrapers between the data center level Prometheus as our monitored task count increases. Obviously, the single task might run into machine limits, like the amount of CPU you can execute your tasks on. So sharding all that up becomes a very attractive solution. This is a very common Google technique for making things get bigger. In fact, if you are doing a Google interview and you don't know the answer to the question, you could just say, I will put shards in there, and they'll go, so Prometheus is just a YAML file. There's some YAML. I want to put a label on everything I scrape. I want to say where my rules files are. There's the DSL that says how to do the arithmetic, and then the scrape configs describe how to find the targets. Like I said, it's cloud native, so you can say either a static list of host names and IP, port numbers, or I can get the list of targets from anywhere, whether it's a interactive service discovery system like Consul there, or serve records, or I have to reload config files that, say, Puppet has generated. Okay, so the time series themselves are vectors of numbers, and they have lots of labels on them, because our service can be lots of different components running on all over the place, different machines, different data centers. We want to be able to query any one of these things, or groups of them, and we want to be able to perform computations on them. So we have a few requirements that ends up with an object called the time series arena that is like a big glob of memory with all the data points in it. But there is some structure to it. If every data point has the form of the timestamp and a value, and they're in lists called time series, the time series can be identified by a set of labels, which is key value pairs, and those key value pairs are just arbitrarily long. So we can have the name of the variable and the maybe the error code. The name of the variable is errors, but we would also like to add another label saying the type of error that happened. The data in Prometheus is immutable once it's arrived into the time series arena. So imagine that there's a big array of numbers, and the labels go horizontally or out into the audience, and the delta t's between each scrape going back in time. I'm oversimplifying this one because we don't really quantize the time series data points like that. They're stored alongside it. But if you want to visualize it, just a big matrix of numbers is quite useful. So labels in Prometheus and in Borgmon come from the name of the target itself, like the name of the job, what instance it's running on, like the machine name and so forth. The metrics that are come out of the target itself. So if the binary says I wish to export the errors metric and break it down by code as well. The configuration in that YAML file, we can say this is the Prometheus that's running in the US West data center. This is the one that's running in US East. So anything that either of those two collect, add the location label to it. And the processing rules that we'll talk about in a little bit can also add labels. So let's do a quick walkthrough of what they look like. So this is an instant vector. It's the most recent in time for each of these time series. And we can specify partial label set matches to slice and dice. So we can ask for just the errors metric and get those ones. We can ask for just one zone and get fewer. And we can be very specific with what we're asking for. All right, so now we will talk about how to write the maths, actually program a Prometheus instance. So we create these things called recording rules, and these are basically saying I would create a new metric, a new time series that has this name, and the way we'll compute it is by doing these mathematical operations. In this case, we want to say the 10-second rate of requests comes from doing a rate over the last 10 seconds of the request variable. So we might have 2 data points in the last 10 seconds, and then we get a single data point in the new time series for each of the labels. So there's like high fan out. The parts of the rule, the language itself, there's a variable reference saying what we're going to query out of the time series database. There's a range expression, so we can go back in time. We want to find everything that happened in the last 10 seconds. There is the function that gets applied, and then the recorded variable. Now this is using Google internal naming convention, and I've heard a rumor that Datadog have a similar naming convention, which I find pretty interesting. We have a level, which tells us at what aggregation of the stack the rule represents. So we might say there's also a data center level 1. There's the operation that gets applied. So we can say that this particular variable is the result of a rate over 10 seconds operation. And then there's the name, what it's actually referring to, where did it come from. So there's 2 types of rules. There's the aggregation based on the topology. So we can build up this stack and say there are individual tasks. We care about individually what their request rate is. But we also care about the whole data center job, because in aggregate, that's doing one function. And so we want to think about that as a single unit sometimes. And then if we have a multi-data center service, then we also might care about the global QPS to that service, global queries per second. Oh yeah, I just talked about that. The other type of rule is the relation builder, where we say at the same level, these 2 variables have a relationship that we care about. So we might say that there's an error rate, and we want to compare that to the request rate because some percentage of the requests end up as errors, and we've decided that understanding how often we are serving an error instead of a response is something that's pretty important. In Prometheus syntax, we can join. It's like an SQL join, but it's more of a vector join, I suppose. But we say this is how you're going to match the 2 sides of the expression together. Sometimes your expression might have higher cardinality on one side or the other, and you've got to tell it how to resolve that. So here we might say, let's pretend, I'm not sure if I have a slide about that. No, I didn't. I deleted that bit. Okay, if you recall back earlier to the metrics export page, I said that errors had a code label attached to it. So we might say that we want to retain the code label in the resulting expression so that DC errors ratio rate 10 seconds also told us the ratio of every individual error code. And we'd say group left to say, make sure that the left-hand side of the operation takes precedence. I'm not sure if I explained that very well, but I can show you an example. Right now, in fact. All right, let's see how well this goes. I have a microservice architecture running here on my laptop. It is I'm just running 10 web server backends. Their job is to respond to a /hi with 200 OK. with a little bit of delay to simulate a database connection, and sometimes they fail. And then there's a load balancer that just round robins between all the backends. So it's not very clever. It's certainly not a production-ready microservice. But it is very good at doing what I need it to do. I can send it some load using Apache Bench. There is, whoops, that last one. There we go. So here we can see Prometheus has got all my targets. They're all up. Excellent. We can go look at the rules I've got configured here. It's not very readable, I admit. I mean, to you in the audience, obviously, if you're sitting very close to the screen, this is incredibly lucid, I suppose. Not like me. But we can look at the job request rate. I'll click on it here. It'll show a little chart. I might zoom down a bit because we don't have an hour worth of data yet. But you can see I'm doing like 50 QPS-ish. And the load balancer and the green line is the sum of the backend servers. And as they track basically identically, modulo monitoring artifacts, then I can say that everything seems to be working pretty well. Now, I might want to, I'll just show you this one. The load generator is a thing that runs Apache Bench with increasing more amount of traffic. And I think I run like 20 of them at peak. So it's not very pleasant. Oh, we've got Alert Manager hooked up. So right now, no alerts firing. That seems pretty good. Oh, no. Already. That's very good. So Prometheus here, we've got our alerts dash. And we can see that of the 4 alerts I have configured, latency too high is firing. Now I can also fire htop. Oops. Yeah. And I'll just kill that one. We can see that the load balance is not very happy anymore. If we reload the alerts. Come on, demo. I shouldn't have showed you that. I hadn't tested it. But we can see that Prometheus knows that it's not there. Anyway, the latency too high alert is the interesting one because I've programmed it with the rule I said earlier, which is, sorry, I'll just go back to the configuration rules. The latency too high alert, it's down here. I've said that for this particular service, I want to record the 256 millisecond bucket, and below is the threshold at which I say that requests should have responded. And so I've got here just taking that one line out of the latency bucket rates and dividing it by the total count of requests in that total bucket at the time, and that gives us a percentage of requests that have fallen into that bucket and below. Does that make sense? And then here the alert is if that falls below 9 fives, then time to page, because that's our SLO for response time availability. And obviously we're paging quite a lot. Now, I think this one's pretty interesting just to look at. This is similar to the chart I showed earlier, but if I strip all of this off, and just job equals load balancer. Oh, that was weird. Sorry. This is the rate of requests arriving at each latency bucket. And so I think we can see that as time goes on, the smaller buckets basically get drained of all requests as requests take longer and longer and the service collapses under its own weight. There's the 8-second bucket. There's the 16-second bucket. As they all go to 0, which is pretty bad. The infinity bucket is the only one with all of the requests left. So, wow, my service is not doing very well at all. Anyway, like I said, the error ratio too high has gone up. That's what I expected to see. Now that we've got a whole back-end job is dead, like an additional 10% of requests are failing because my load balancer is not very clever. And so we can see that it's saying that the error ratio is quite high as well, so we should page for that. So there, latency too high. And we can go to Alert Manager, which would nominally be routing our request to the final destination. I haven't got it set up to send anywhere. But you can see that from here I can see that both the server backend job and the load balancer job are paging for error ratio is too high, and the load balancer is saying the latency is too high. I can just click on that and get some more information out of it and link back to the thing that sent me the alerts to say this is what the conditions were at the time of the alert. So, with a little bit of polish, you can get some really nice UI going on. So yeah, that's the demo. It is very easy for you to spin up time series-based alerting. It's like 10 lines of Prometheus code. It's maybe 30 lines of Go to make a service that is not very good. So to recap, the thing I really want to stress, I don't want to particularly say you have to use Prometheus, although that would make me quite happy because I think it's really cool. I'm not going to say you don't use Nagios anymore, but that would also make me happy. I really want you to use higher level abstractions to reduce your maintenance cost. Once you find yourself doing the same thing over and over again, you shouldn't be doing that anymore. We have computers for a reason. This is the same paradigm that configuration management did almost 10 years ago. People don't want to edit config files anymore. We can make robots do that for us. I'm not going to talk about the big data thing. I think that's a silly line. I should have removed it. But definitely, if you're going to revamp your monitoring, you should also be considering what it is that you should be paging yourself for. And I want to stress, this service level objective model is a really good way of thinking about what matters to the business so that you page for stuff that your boss or your CTO wants you to get paged for. Because that's what really matters to the company. If you're paging for anything else that isn't going to have an impact on the business, then you should ask yourself why you're doing that. And probably senior management are going to ask you why you're doing that, because they don't really want to pay you to do the things that aren't going to add value to the business. And I don't really want to have a conversation about adding business value because, A, I'm not an expert, and B, I think that's terribly boring. But in your own mental health's best interest, getting paid for very few things that actually matter is a much better way of living than getting paid for everything all the time. So do that. That is the end. There is these two papers, My Philosophy on Alerting, Achieving Rapid Response Times in Large Online Services. You should use a search engine. Go find it. The source code for the demo is the third link. Prometheus is the second link. My email address at the top. I didn't use the poster, so ignore the copyright notice. Thank you very much. And we can take some questions, I think.
So can we use the alert manager other than Prometheus?
Yes, you can. It is a independent product, independent binary. It has a well-published API, so you can use existing tools that talk to it or write your own tools to send alerts to the alert manager.
Thanks.
Documentation is on the Prometheus website.
A common objection to SLO-based alerting is that people say if an SLO violation is inevitable, we should alert before we violate the SLO so that we can take action to prevent the SLO violation. What's your answer to that?
Yes, you should. I don't have a good answer for that. I like to live in a fantasy dream world where the SLO is going to prevent us from actually getting the severe outage. I'm going to wave my hands and say there's like resilience engineering going on where I'm getting paged for loss of capacity to the point where now it's an emergency, but the users are not impacted, but the business does care a lot. I care a lot. Let's say I have 2 data centers. One of them fails. The service is still running. I really want to be paged for that data center that's failed, but it's not yet a user visible impact. So maybe like that. This is not really a monitoring problem, but a whole systems engineering problem. All right, thanks a lot. See you around.